Good afternoon. Afternoon. Today, I will be talking about what page analysis is studying. Sultan Ismail Mosque. Discuss on paper by this begin. This 2006. Interestingly, this is actual study. So they already the profit system, but that system is proposed by the Institute of Environmental Water Resource Management in UTM without taking account into the water cascade analysis or pitch analysis. So by doing water cascade analysis, we found that the water saving for the carbon system is below average. They can actually save up to 85% of water. And this exercise is, although it's relatively low, but you can also use it in your company. That is similar. What I've done, I told you it's 2 weeks. Step by step, it's similar. Different is case study. At the end of this lecture, I have one exercise to try. It's based on paper mill case study. For that exercise, I will give you 30 minutes. The computer will ask about ways how you calculate it. Question during the time. So for this water pinch analysis, one system, this case study not just we do pinch analysis, we also do water regeneration. This is a slide number 5. So for your final exam, Farid asked me to send my question on Monday. Last The question is about gas cascade analysis. So this year it's water cascade analysis. You can also refer to this paper, the 5. For the urban sector, tribute significant percentage of consumption, particularly in developed countries, warmer climates. Indonesia, for example, this is from the picture, page 2. Indonesia, for example, the domestic sector contribute 60.1% total water consumption. The need for efficient water management in the urban sector is becoming ever more crucial. Due a sharp increase in the price of fresh water. This trend is likely to continue in the near future due to predicted shortage of fresh water and hence the possibilities of resorting to wastewater treatment, desalination, groundwater extraction, and the state water purchases as well as the transport. So the majority of work on urban water conservation is focused on design of water segregation and wastewater recycling. So in a water distribution system, it is possible to determine the maximum water recycle flow rate to appropriate water cascading, and not that the maximum water recycle flow rate corresponds to minimum fresh water consumption. The first key step toward minimizing fresh water consumption and wastewater generation is to establish the baseline minimum water consumption target. So, so the first key step here is actually pinch analysis. We determine the minimum maximum water recovery or minimum water usage. So as far as our research has revealed, is the description of how the water cascade analysis technique was adopted to establish the minimum water targets for the Sultan Ismail Mosque at the University Technology Malaysia. So for the final exam, it's water cascade analysis. It's not meeting composite curve. Last year, yes, we meeting composite curve SCC for gas pinch analysis. Fresh water is stored in 4 interconnected current water distribution network for Mosque. So different historic mosque, the BTN is on the hill next to faculty architecture and library. The ablution water or rainwater were to be filtered for solid particle like using fresh water is stored in four different distribution tank, each with volume. They have four tanks to store the fresh water. So fresh water here refer to the municipal tap water. So this tank are arranged in a straight line, so the fresh water will fill up the first tank, overflows into the next tank, into all four tanks. The estimated total freshwater consumption for both is 11,000 per year. This value you can refer to this. Of this 9,178 per year is used for pollution, and the rest is for toilet flushing, irrigation, cleaning, was this apps. The total amount of water consumed varies throughout the year between semesters and monthly, of course. During the semester, meaning the undergraduate is inside campus, the amount of water consumed for ablution is about 16 meter cube per day. It's a lot. On Friday, but only 25 meter cube per day on other days. Friday because of the Friday prayer. So in order to estimate a reasonable typical water saving for the mosque, daily water consumption calculation will based on normal semester. So assumption, not assumption. The calculation for this case study is based on normal semester. So from the 11,550 meter cube per year of total fresh water consumption, 86% is for ablution, and the rest 14% is for other kitchen, shower, irrigation, mosque cleaning. So this system is proposed or retrofitted already by IWRM, Institute of Environmental and Water Resource Management, ITM. So the retrofitted network design, so the ablution water is the they propose to reuse ablution water and to be filtered for solid particle like hair, stone, and dirt before going through a series of treatments using activated carbon and microfiltration processes. Since the water output was approximately 29.07 here study for ton for the four tanks, only 7.27 ton per day of treated water can be fed into the last distribution facilities. This design allows an estimated fresh water saving of up to 25% compared to experience of about 10 years. So later we see, but it's not included in the paper, but they did mention how much we need to treat the water after the cascade analysis. How much we need to regenerate the water is based on the back period. How long we can get there when we back. So from this method, see here, red water and ablution water. We go through the treatment. So in this paper, the treatment is activated carbon and microfiltration. So the one that in the install the water dispensers and this we one is ultrafiltration. So microfiltration is below ultrafiltration. Filtration. Pasti. So the so about during the rainy season. So during the rainy season for the IWRM method is one. During the rainy season, the rainwater was collected instead. The spent efficient water will be diverted to the sewer. So they will use totally rainwater goes to the treatment. And the pollution water will be diverted to the one. So this design allow limit fresh maximum. So for this study, there are many parameters we can represent the water quality. Because this is case with multiple contaminant. So for multiple contaminant, you need to find one analysis that can cover all of them. In this paper, in study, they choose BOD reference. So for the molecular oxygen demand was the most significant water quality factor chosen for the water use. Fecal coliform, one of the was not selected as the quality factor since the minister was proposed to not only the water. Regeneration consists of three main steps. Firstly, greywater is filtered for particle. Next is passed through activated carbon to remove present odor. And then chlorine or UV is used to disinfect the building. The most statistically so if you refer to page page 6 of paper number 5, we show you table 1 and table 2 summarize the water demand and source proceed. So water demand is incoming so water demand is incoming fresh water. This is the demand. The water source is after the activity. So activity here, which are wash basin, shower. This is say is this is the so water demand is actually equal to sink. So demand is sink. Similar. This is the fresh water, clean water. This is the use water or contaminated water. So table 1 and table 2 summarize the water demand and source proceed. There are 8 water demand and 6 water source. Water demand is coming. Water source are just available for possible sampling, while water demand reflect the actual volume for various water using processes. So black water from toilet flushing, toilet pipe was not used as a water source because since it is highly contaminated, it will be different from this, while water from irrigation is assumed to be completely resolved powder with salt. So for table 1, to page 6, paper 5. So table 1 were adapted from US EPA standard of water reuse. Table 3 is next page 7, which stated clearly the BOD. And the data for water source in table 2 are based on data by referred 21 and 22. Table 3 shows that the US EPA set a conservative water quality standard for WB level to be reduced at least. So minimum is 10 ppm. Maximum is 10 ppm for non-potable domestic water recycling. So non-potable water refers to water that is not used for human consumption. Since all the water usage after, that's why when you see the table 1, okay. So that's why when you see table 1 here, for kitchen, cost 10 ppm maximum for non-potable water. Not for human consumption, but also for kitchen, the BOD concentrations will be 0. Clean water, sorry, drinking water standard. Okay. So the Mosque case study is strictly speaking a batch process. So this is a batch process since all water usability occur in discrete time period. However, in this case, it is possible to use the WCO technique to look for a continuous process to establish minimum freshwater consumption and wastewater generation target. The availability of storage and spectrum of water utilization allow the Mosque case study to be modeled as a repeated batch process that approach a continuous system. Although the usage of water in mosque mostly use water certain time, but since it's occur in stipulated time within 1 day, 1 week, they assume it's somehow look like a continuous system. First, the total. Now we go to water targeting music, WCA, strategy and result of the case study, page 58, page 58, number 5. Uh, so you still remember there are 5 steps of the water analysis. So the first step here is a total building review is carried out to have a good understanding of the plumbing sanitation and building. Next is the data acquisition and extraction conducted by surveying the water flow rate and patrimonial source discharge. So the second one here is referred to the mass balance. While this data, the process flow diagram of the initial water network can be obtained from the step 2. Subsequently, WCA, water cascade analysis, is constructed to achieve the true minimum target for the water network. Finally, a new water network is designed for the economic analysis is carried out to show the total savings of the new water network. So finally, a new water network design. Okay. So once you determine the true minimum target or pinch water system, then you can do the water network design, meaning which stream is above the pinch, which stream you want to filter. So the main objective of the WCA is to establish a minimum water target, the overall fresh water requirement, and the wastewater generation process. So looking at the possibility of using the available resources, we can study the demand. To achieve this objective, one has to establish the problem class to see the different water quality level within the process of the study. The interval water balance table has been introduced for the purpose. The most study described the when you see the water targeting. The first step in the WCA is to set up the interval water balance table for fluids. To determine the net water source or water demand to level. So the water source and water demand refer to the table 1 and table 2. So how they get table 1, table 2 is from the process flow level. So the first column of table 6 contain the contaminant concentration level. This column refer to here concentration in ppm. So in ppm, you have many 10 here, 10 ppm for the water demand, water source, that's the water seed. Then summary of the water source. Please, the variable vary because after you, for example, for kitchen, although the incoming is 0, using plain water, then after usage, see here the BOD up to 506. Okay. So example 10, we have 10, the lowest is 0, then 10, yeah, already 10 as well, and 23, 28, 16, 472, and 6. So each concentration level is expressed in terms of the water purity. The second column, this is the water purity calculated by this equation what? With the fraction of pure water set at 1 million ppm, the fraction of pure water in a calculated stream, or the water purity can be expressed as 1 million minus C over 1 million. So 1 million because it's part per million. So it's like a percentage. So percentage is over 100. So for ppm is over 1. We see is the contaminant concentration in ppm. For column 1 is concentration, column 2 you need to include. Example 1, how to calculate, how you get 1 here. So 1 million minus 0 over 1 million is 1. Example this one, 1 million minus 10 over 1 million, we get 0.9. This one is 1 million minus 556. The number of purity interval was the number of water source application of equation, this equation 2 to the most case study, till 6 purity level. Next, the water purity different to the column 3 of table 6. and put different plus one. What happens will be Pn minus Pn plus 1. So the totality is within, yes, sorry, between the polythene. So 1 minus 0.9999 is equal to 0.00000. 0.999 minus 0.999. Now column 4 and 5. So delta P how to calculate is En minus En plus 1. So N here refer to the interval. How many intervals? So how you know from the interval here? You calculate the number of concentration in this case. So we have 0 is 1, although we have many 10, so 10 is 1, including water source, 10, but still 1 interval. And we have 23, 26, 6. What means 5. So when you refer to this paper, make some correction for the table 6. Instead of a negative, so for the column 4, instead of negative 9.07, it's actually negative 29.07. It's for water demand. Why? Because you need to calculate 25.03 here plus all the D3 until this end. Because all of it is from the same concentration, ppm. So the total amount for water demand at 10 p.m. is negative 29.07. If you refer to table 2 here, 10 ppm, the source is 11.14, only one. But for 23 ppm, is 25.03 plus 0.14, then you get 45.17. This is a summation. And similar concentration, you sum up. The formula contain the total flow rate for the water demand in water source. Flow rate of water demand is negative and source positive. This flow rate sum up at each multi-level to give the net interval water flow rate. The 6 here. There will be so plus sign represent the net water source minus. So how in the column 4 and 5 is clear, because on table 1 and 2. And don't forget for 0 ppm as well, it's negative 0.03 reduction. For the column 6, it's just a summation for demand and source. For example, here it's negative 3, because there's no more demand, there's no source. For 10 ppm, it's negative 29.07 plus 11.14, then we get negative 17.83. It's negative, so it's a demand, not what the demand. And the rest is net water source. The rest is so we have the interval water balance table. So from this interval water balance table 6, can check what do the cascade analysis. The next key step is the WCA with the cascade analysis. Is to establish the freshwater and wastewater target for the process. So in doing so, it is important to consider both the water flow rate balance and the concentration driving force, so that the true minimum water target can be obtained. So the water flow rate balance involves using the water cascade figure 7 and figure to get the cumulative net water source of the one process FC. Conceptual illustration of how one cascade will minimize. The figure 8, this one already covered. Sure. Those with paper, you can refer to page 1. For the water cascade diagram in figure 7a, this figure, so we have A here is a water cascade, B is a pure water cascade, C is the interval fresh water demand. Fresh water flow rate, W of 0 here, is assumed. This is normally we do water cascade analysis. We start with fresh water as 0, then we find the maximum recovery pinch. Here, the net water demand of 0.03, the first spirit level is cascaded. That's why they said, that's why the word cascading is 0.03, that's so it started here. Since it's 0, so it's forward to 2023. Okay. Consider to the second plant level to meet another water demand of 17 to 17.3 ton per day. Giving a cumulative net of 17.96 in demand. This cumulative demand meets only net water source down to the next 4 plant level to yield cumulative water source or wastewater flow rate of 7.67 ton per day. It's about this day. Cascading it. How to cascade? Plus. Plus 0.02 plus. If we keep like this, it's plus 25, we don't say that it's plus, 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 plus. We get the stuff of it. The lowest to so the communities net water source or demand or FC here. Each coaching table form like integral water basket diagram. Water basket diagram is similar to the integral picture. Water cascade diagram depicting the preliminary water balance fresh water flow rate of 0 ton per day. So basis to generate physical cascade and ultimately the minimum water target. But again, that in addition to considering the flow rate valence, the true minimum target can only be realized by authenticated on the pure water surplus or deficit, which is a product of the cumulative net water source between from the company across pure benefit level. So pure water surplus and deficit here, you can say value. To get this value 0 ton per day is not 0. 0.03 times 0.0001. is 0.000000503. What is something? It's 3 times 10 to the power of 27, 60. So they choose to put 0 times per day. Although it should be 3 times 10 to the power 7 times per day. Page 61, paper. The pure water surplus means that water is available with quality higher than what is concerned. On the other hand, a pure water deficit means that water of higher quality than those available is required. So cascading the pure water surplus deficit down the quality level 0.0023 times the difference 0.00013, you get 0.00024. So that's repeated. So cascading the pure water surplus deficit down the pure water cascade represent negative amount of water surplus deficit. This one. So the cumulative water pure water surplus deficit at each purity level is a numerical representation of the water surplus diagram introduced by Halal. This graph is water surplus diagram that shows insufficient pure water in the network proposed by Halal. So what happened is for this diagram, you need to increase the water flow rate until it reach the purity level 0. So once you shift it, then you can identify the pinches occurs over here at 0.0597. This is water surplus diagram. It's different method, but at the end the output is similar. But there are some advantages of using water cascade analysis compared to water surplus diagram. So notice that for pure cascade in figure 7b, cumulative pure water deficit observed in second to third kilometer here. Static. The deficit on the this deficit means that there is insufficient is negative here. Instead, insufficient fresh water in the network result are the result of the swimming of the zero fresh water level. Why you get negative here? Because of zero time per day. Water cascading, just additional fresh water should be supplied to remove all pure water deficit and yield sustain feasible pure water cascade. So fresh or pure water is to be supplied at the highest purity level. To minimize fresh water, it is necessary to determine the minimum flow rate of fresh water or even fresh water demand. It will satisfy the total requirement at purity level. The interval fresh water demand is still a physical pure water cascade after network water network. Figure C here is the interval fresh water demand with flow. So, fresh water interval fresh water demand FW K for each purity level K is obtained by dividing the cumulative pure water supply to this value with by the purity difference between the fresh water supply in FW and purity level liters. So in this case, the fresh water will be assume it's the highest purity is what? 0 ppm is 1. By using this equation, example how you get 0.03, because this is not 0, it's actually a negative 3 down. Time 7 time per day. Total 1 minus yeah, it's really you take 10.16 ton per day is 0.00234 divided by 1 because pure fresh water concentration solubility is 1 minus pK of liters is 0.99997. Okay, we take 10 if we calculate using the calculator, it's actually we take 10.70. Mhm. Now page 63, goal number 5. So referring to figure 7C, a negative value for interval fresh water demand means that there is insufficient fresh water, whereas positive interval fresh water demand, positive start at purity level 4, means that there is excess fresh water at the purity level K. This case, purity level 4 and above. In order to ensure that there is sufficient fresh water at all points in the network, a freshwater flow rate of exactly the same magnitude as the absolute value of the largest negative in interval freshwater demand, which is 10-16 times per day, should be supplied at the highest purity level of a feasible water cascade. So meaning we will use this value, add it as the FF, the freshwater flow rate. So the FFW4, this one, 4, FW of 10-16, 3 is found at the third purity level P3 of the cumulative freshwater cascade in 7C, figure 7C, as the largest negative interval freshwater demand. So this quantity of freshwater is at the highest purity level of the visible water cascade in figure 10. You notice here, the 10-16 ton per day is freshwater input for this system, and automatically the largest negative here tadi turn to pins or zero. So note that visible water cascade is the one that result in positive of this 0.3. It's a plus in the water cascade. So the minimum water cascade analysis through minimal flow water FW and what's water flow rate FWW target 10/16 ton per day and 17 ton per day. So compared to before the cascading, sorry, before the pins, 0 ton per day, wastewater produced 7.6 ton per day. After the freshwater feed at highest purity level here, the amount of wastewater increased to 17.3 ton per liter. This is the optimum. So at the third purity level, PG 9997, figure 10, where there is a zero accumulating pure water surplus to exist the pinch of the most problem. So once you change fresh water flow rate here. In theory, calculate the cascading. For example, how to calculate this? So 10.16 plus negative 0.03, you get 10.13 plus negative 17.13, you get negative 7 plus 25.17, and so on, until you get the wastewater flow rate. 17.23 times per hour. So the pinch is the most constrained part of the network. Exact maximum of the volume. The detailed network design proposed by Castro et al. From the Institute Latin case study. So note that through the WCA we have obtained the utility target ahead of design and are able to verify whether the proposed initial design achieved the maximum water recovery objective for this plant, for this mosque. The water cascade and pure water surplus cascade diagram can be integrated with the water cascade table 7 through the WCT water cascade table. The WCA technique offers two key advantages over the water surplus diagram. So water surplus diagram is the graph proposed by Harley. In realizing the minimum water target, apart from the power to eliminate tedious alternative step of water surplus diagram, to reveal the exact utility target in each location quickly. So the first key advantage in WCT water cascade table clearly display both the minimum freshwater and wastewater flow rate. So you can determine the freshwater FW wastewater from the water cascade. In the cumulative net water source demand column, you see this one. Note that in the case of the water surplus diagram, only the minimum freshwater target is known. However, the value of the minimum wastewater flow rate target is not available from the diagram. The second key advantage of using water cascade table is the is that it enables a designer clearly to identify the pinch causing stream and the exact water allocation position above and below the pinch if the minimum water targets during network design. So referring to table 7, zero cumulative pure water surplus, the purity level 0.9997, P3, purity level 3, represent the pinch point that the pinch causing stream which exists at this purity level is the water source. See the pinch, follow it. Water source with a total flow rate of 25.17 tons per day. Water source is after usage. Refer to table 2, 33 ppm, 21.17, 25.03 plus 1.93. Referring to table 2, this stream originated from two water sources, the ablution S2 and the wash basin S3. So from here, you can actually identify which source is the pinch. So in order to realize the pinch point and to achieve the maximum water recovery objective, a portion of the pinch causing source stream, in this case the emission machine, has to be allocated to the process above the pinch. So this value here, it should be treated above the pinch, while the rest to a process below the pinch during design. The exact water allocation is available from the WCT. Referring to the cumulative net water source CU of table 7, out of 35.17 ton per day, water source contribution was seen 7.8 ton per day here of water found between P2 and P3 must be sent to the region above the pinch. Negative signs indicate sending water across the pinch. On the other hand, 17.37 below the pinch must be sent to the region below the pinch. So FC here is a cumulative water. So such important insight on pinch causing stream, water allocation evident from WCT, but are not available from the graphical technique of the water surplus diagram. With the water supply diagram, it is necessary to construct a balanced composite curve to obtain the exact water allocation target. Red one is for water pinch or maximum water recovery objective without the water regeneration. So now we go to the water regeneration using WCA, water cascade analysis. Until now, I haven't given any final exam with the regeneration. It's not just determine the minimum recovery. So two possible scope for process changes to reduce the water target further. Hence, water consumption include water regeneration. Okay. Water regeneration involves the partial or total upgrading of water quality using purification techniques such as wastewater treatment like microfiltration, greenhouse filter, sand filter, with heats, multimedia filter, biofilter. So the regenerated water can either be reused in other water using process or recycled to the same process to reduce water consumption. Wastewater generation subject to the concentration. Concentration. And by how much you need to treat, that one is based on the cost. Calculated based on the So to increase water availability, Harali, one that propose water surplus diagram, propose the use of water composite curve pinch quality to guide the regeneration of the surface quality. This is the rule of thumb to choose which region you want to do the regeneration. Example, regeneration above the pinch. For this case, above the pinch is negative 7.8. Water source in the region above the pinch are partially treated to upgrade its purity. So at the moment, negative 7.8 is between P2 and P3, 10.23 ppm. So we try to treat it above its purity to upgrade purity. Next is regeneration across the pinch at 25.17 there. This one is for you. Across the pinch. So water source in the region below the pinch are partially treated to achieve purity higher than the pinch purity. Next is regeneration below the pinch. Here. Water source in the region below the pinch are partially treated to upgrade the purity. However, this one you need to note. The upgraded purity must be still below the pitch. This is the rule of thumb for targeting which stream for regeneration. So regeneration above and across the pinch, we have three regeneration target. So for regeneration above and across the pinch, will reduce the fresh water consumption and wastewater generation. While regenerating below the pinch will only reduce wastewater generation. The main problem of dealing with process changes is that an assessment of the impact and changes involve repetitive ability to revise the utility target and relocate the pinch. Such tasks can be quite cumbersome. The absence of efficient targeting tools. WCA has managed to overcome this problem through the introduction of the WCT. It's very recommendable. So table 7 shows the pinch concentration for the most elevated at 23 ppm. Only this line. 23 ppm. One possible option of regenerating the water source is to treat the ablution water to a position above the pinch. So in the paper, page 65, and et al. Propose treating domestic wastewater using microfiltration to reduce the contaminant concentration of DOD from 59 ppm to 4.2 ppm. And also other contaminant concentration table 8 suitable for use. So table 8 we can refer to page 66 the paper. So table 8 shows the in influent and effluent and water quality after the microfiltration. There are many diseases here. They interested in the audience. So since the incoming is 59 per liter, after the microfiltration, the concentration reduced to 4.2 milligram 4.2 ppm. However, the amount of ablution to be treated depend on the cost of the treatment equipment and analysis of the relationship between treatment equipment cost, flow rate, and the known amount of water needed to be treated that has an appropriate payback period. The total amount of ablution water to be treated using microfiltration is set to 727 tons per day. So 7.27 tons per day is based on this case study by IEWRM. So they install microfiltration. So the amount that is treated is 7.27. So by choosing 7.27 with application of the payback period, 10, 10 days. So table 9 from WCT shows the new pinch breaking 0.999977 ppm. In the freshwater and wastewater flow rate, it used to 4.22 day and 0.89 ton per day respectively. So, so here you can see 17.9 plus 7.27, 25.17. So 25.17 from the water source, they regenerate. So by regenerating, it produces 7.27 ton per day with concentration of 4.2. So meaning the water source now is reduced. Instead of 25.17 or 23 ppm, we refer to table 2. Then you have different water basin. So in this case, the ablution water is hooked to water filtration. Only part of it, 7.27. The rest will still 23 ppm. So from here, the fresh water source instead of 10.16 to 2. So, so for the table 9 here, actually you need to start with, this is the after they identify the pinch. So before they determine the pinch, they will still use the here, but the freshwater feed is 0. That one you need to bear in mind. So whenever you started your water cascade, even after the regeneration, meaning you have another stream here at 7.27 and significantly reduce the amount of 50 ppm, 20.9. You need to start with 0, calculate, then you get the negative water surplus with negative value. The highest negative value will become the pinch, become the reference for the how much fresh water need to be inserted in this system. So in this case, the highest is negative 4.22 here. Doesn't show. So you need to calculate again until interval freshwater demand FFWK before you can choose the amount of minimum freshwater flow rate that need to be added here. 4.22. You refer to figure 7A, they have water cascade, your water cascade, and interval freshwater demand. Okay. So designing a network that reuse wastewater is needed due to the shortage of fresh water and rising cost of wastewater treatment. Reusing, regenerating, voting on reuse wastewater reduce freshwater consumption, reduce water generation. The wastewater can be reused directly in other water using operations. This reduces both wastewater and freshwater volume without changing the mass load of the river. So in comparison with the previous retrofitted system by REWRM, which predicted 25% of the saving and was predicted 30%. So by using water pinch analysis, which method, this method predicts 65.1% fresh water saving and 51.5% wastewater generation before the regeneration. Just simply optimizing the water to determine the exact amount of fresh water needed for the system. But after the regeneration, by installing the microfiltration, the water saving for fresh water is up to 85.5% and reduction of 67% of wastewater reduction, which is very significant by combining regeneration with water pinch analysis. Amount of wastewater, what fresh water saving is a lot. So with regeneration, both the IEWRM, water pinch method use microfiltration treatment. So meaning the payback period will almost be the same, except for the original piping system. However, the water pinch method gives much better fresh saving. So in the worst case scenario, there is no rainwater due to drought season. So omitting rainwater as a source and going through the same preparation using the water cascade table with partial regeneration of emission water as previously, a potential water saving of 63.9%, wastewater reduction of 70.5% are targeted. It's still better than the system proposed by EWRM. So WPA water pinch analysis can target the minimum fresh water and wastewater flow rate before design, while the IPWRM method need to design first before knowing the total fresh water and wastewater saving. This is the difference between doing the pinch and doing the pinch directly designing. So with WPA, one can efficiently and systematically plan savings, able to identify inferior design option knowing the target and maximum potential saving design. In order to determine the best possible design can be the most effective. So without this design target, the designer is unaware of the potential saving until recycling. So conclusion, now that we know how to conduct the brief, it's an idea, try and copy. So that is all for the case study. So for the exercise, this paper mill process. So later on, the final exam is based on water cascade analysis. This exercise. In this paper mill process, this paper is fed to the pulpers. It is blended with distilled water and chemicals to form pulp slurry or stock. The paper sheet formation begins when the paper stock from pulpers is the forming section of the paper sheet. Figure 3 shows that total 986 tons per hour of fresh water is with the water too. So 1 plus 22, we get 96.42 tons per hour. We remove the debris while the water is removed from the stock. Gradually, the sheet production. So we have pressing and forming the paper sheet. So part of this water source, see here the term water source, 5 and 6, and then say the right thing along with the second water, 9 here. From other process in the beginning purpose of the IP. To remove printing ink from the main stock, the inking pulper, the IP, is fed with 751 751.22 tons per hour of fresh water extremely and 398.5 tons per hour of used water from white tanks 50. The mix fresh water ultimated water 1 liter. Of the deep source, the IP source, and the liquid alpha source to equal 54 tons, then mixed with 14.7 tons of fresh water stream level. To dilute the stock will pump to the decorator in the approach flow system or AF. The freshwater stream 10 is also used to dilute de-inking chemical here in the chemical preparation before the chemical sent to DIP unit to assist in removal. In addition, other process in DIP in others here also received 201.84 tons of freshwater soda water. Same for as for wastewater collected from the preparatory in DIP and to the effluent treatment before being discharged in so wastewater purpose is 1680 ton per hour. So this is the table showing water demand associated with this case study. This is the water network. To calculate the minimum energy target for the peppermint using the water cascade statement. So your task is to construct tables. Now you have the data for what still demand resource. If there is no table 1 here, you need to extract it from here. Now you need to construct the interval water balance tables. You refer to table 6 in paper number 5. We have seven column. First one is the interval. So determine the interval first. To determine the interval, you refer to the how many concentration without the duplicate. How many concentration, then you know the level. Then you arrange the concentration in ascending order, the table, from 0 to the highest ppm. Calculate the purity, delta P, determine the summation of demand resource, and determine the total of demand resource. You do that for 10 minutes first, you check again. So any question? We have so this example when we change the distance. So for table 6 here, sure if anyone have done it. So for table 6, we identify the concentration after from 0, then 220, 80, 100 in ascending order. Then 170, 200, 230, and 7. We have 7 interval n equal to up to 7. This is an example of table 6. So for concentration, started from 0 until 1 million. For this case, 1, 0, 20, 20, so on, 250, 300, 1 million. For the purity, you need to use equation P equal to 1 million minus C over 1 million. What, for example, for the first interval here, so 1 million minus 0 over 1 million is 1. It's easy. For the second interval, here, so your calculation is 1 million minus not 10, this is example, minus 20 over 1 million. Yes. Million. See, once you calculate the purity here, P8, so for column 3, you calculate the delta P. So delta P is between the difference between the purity, example 1 minus 0.9 millimeter. Column 4, you identify how much is the demand and how much is the source. So for this demand here, you have 220 ppm. So you need to add up 155.4 plus 24.68. Once you determine this, you can put it inside the table. So for 0 ppm in this paper mill study, there's no 0 ppm, so meaning demand and source is 0. So for 20 ppm, we have 2, so 155.4 plus 68 is 108 for 20 ppm. Then for water demand here, we need to put a negative signs. Water source is no positive signs. Then you sum up the demand plus source. You get something like this, and for negative, you find a place of demand. Positive is water source. Once you have the table 6, then you can calculate the cascading. So for cascading, you start with zero fresh water cascading. So for zero wastewater, based on the summation of demand and source, cascade it to get the cumulative water source for demand, FC. So meaning the interval water balance is 1 table. Meanwhile, water cascade is 1 table starting from 0 wastewater. So once you do this, you calculate the pure water surplus or pure water deficit. So to calculate pure water surplus or deficit, what you need to do is so pure water surplus or deficit here is calculated by multiplication of cumulative net water source of FC. So FC times delta P. In this case, delta P is the purity difference. So example here, 0 ton per day here. 0 ton per day is calculated by 0.003 times delta P. It's not 0, we discussed this already. Then after you calculated this, follow it. So 0.0323 here is calculated by -7.26 times delta P 0.00013, then you calculate the cumulative pure water surplus. So pure water surplus is cascade. So here 0, this one should be some value. It's 2 times 10 to the power of -7. Okay. Plus negative 0.00003, we will get this value and so on. This is the cascading for pure water cascade. Then after that, you calculate for interval. So the last one here, the figure 7C, last column, interval freshwater demand is important to determine the pinch. So for the interval freshwater demand, the calculation is based on equation 4. Refer to the paper 5, page 62. So FFW is equal to cumulative pure water surplus over deficit over purity of fresh water at the highest purity minus pK is the purity at any level, depend on just this value. So meaning for the first, okay, for the second year, negative, so the 10.16 is coming from negative 0.000234 divided by highest purity if it's 1 minus purity at level 3 is 0.999977. So once you plug in this value, you will get this negative 10.16 times per day. The method is similar. Now you finish calculating the interval freshwater demand, meaning you can calculate now determine the pinch. The pinch is how to identify is the highest negative. So in this most example, the highest negative is negative 10.16. But for paper mill, it should be different. Okay, next is once you determine the pinch, you need to recalculate using the new, using the pinch point as the freshwater supply, freshwater flow rate, which if you the what a new water cascade. So a new water cascade. So from the new water cascade with the pinch, sorry, with the cumulative water surplus equal to 0. But before you can get this pure water cascade, you need to calculate this one, cumulative water source over demand, FC. So by using the pinch that you obtain from the paper mill water cascade table, you do the cumulative cascading, determine the new wastewater flow rate, determine the pure surplus or deficit using the same equation. Even then you get the pinch. So once you identify the pinch, that is the minimum validity target for the using water cascade system. So you have at least 3 tables. And but if the question asks you to do water regeneration, with some sort of yes, just it should be zero. Should be zero. I'm not sure about what Dr. Farid is doing. Cascade analysis. So from pinch here, if the let's say the question asking regeneration, so meaning we need to determine which point we need to determine which stream that you need to regenerate. Either above the pinch, on the pinch itself, or below the pinch. How to know that one normally will be given to you each stream to focus on? By doing that, you need to recalculate another water cascade using zero fresh water, but with but with uh, but with a new stream. For example, this one, a new stream with uh, regenerated water. So once you have regenerated water, meaning the water source from where you regenerate it must be reduced. Reduced. So with FFW equal to 0 for the first time you calculate after the regeneration, in order to determine the pinch. So once you determine the pinch, you need to recalculate again the water cascade table to get the actual how much fresh water supply needed and how much the wastewater will is reduced. So without the pinch, you have three table. Sorry, without the regeneration, you have three table. With the regeneration, you add up the two table, five table total. So step analysis with regeneration. Yes. Regeneration can pass now. For that example, for this example, the answer is can try it zero. This is the answer. So wait, see the interval here, 1, 2, 3, 4, 5, 6, 7, 8, 10. This is the concentration. Start with 1. You calculate the rating. This is a bit different. Okay. For the concentration here, it's actually should be in ppm. So should be, if you see the value like this, it's actually a purity. So in this case, sorry, just here, this the make some mistake. What should be the purity? This one should be the top purity. Normally we have another, so interval here is actually the concentration. See, interval is here. Look, so we big the concentration. Then we determine the demand and source. So for the demand and source here, for example, 20 ppm, demand we have 155.40 plus. So 155.40 plus 34. 20, yeah. So we get 190.08. For 80 ppm, only one, so 81, then 201. Don't forget the negative for demand. The negative here, well. And for the source, it's straightforward. There's no duplicate. So have 1, 2, 3, 4. 4 values. Then do the summation for demand and source. So for first one, there's no zero. Unlike the most case study, you have 0 ppm for the kitchen. This one, no. Paper mill, there's no 0. So no 0 ppm. Okay. So the demand 0. This one is the. So when you come up with this, it's actually negative 201 plus 155. Yes. So they already found out the pinch now. So freshwater flow rate is what is the FW? This is the FFW, freshwater source. So this is the FWW, wastewater flow rate. This is already demised. Then calculate the pure water surplus. So they mentioned to you how to calculate it. To calculate cumulative surplus, you need to multiply FC, cumulative multi source of demand, with delta P. Here, delta P. Then cumulative multi surplus is actually the calculation as well. Equation 4. Equation 4 is cumulative, is multi surplus and opposite, divided by fresh water minus humidity level K. So fresh water still 1. It's the highest concentration gas and the stable. See it? 1. This is answer for water cascade table without regeneration. Regeneration, yes. So any question at the moment? That haven't in again. If you have any question, you will ask. If you don't have any minutes. By next week, I will give you some exercise. We will discuss it on the last meeting. We prepare you for the exam. Final exam is on 8th September, Sunday. 8th regarding the question, if you have any other question, you can also email me. Okay, so the learn something. It's not complicated, but it's not actually. If you have all the data, meaning a complete process flow diagram, you can basically do what the pinch analysis to any network. Your house can also use it. For the lab, one process possible just to determine the minimum the water required. Although at the moment they have this certain value, if you do this range, so the amount is be reduced. Can also better for you. Since okay, so thank you. See you next week. Maybe discuss the question exercise.